What is a wormhole? A wormhole is a hypothetical tunnel-like structure in space-time that connects two separate points in space and/or time. In the language of general relativity, a wormhole is a solution to the Einstein field equations that allow a shortcut through space-time, potentially enabling faster-than-light travel between distant regions of the universe. The formal definition, a wormhole, also known as an Einstein-Rosen bridge, is a topological feature of spacetime that acts as a bridge between two distant points described by a spacetime metric with a non-trivial topology. Key features are two mouths connected by a throat. Can be a traversable Morris-Thorne model or non-traversable Einstein-Rosen bridge. How do you build a wormhole? To build a wormhole in general relativity, one must design the perfect metric, solve the Einstein field equations, make it safe for travel, and make it quantum mechanically stable. This is quite a challenge. However, the mathematical framework for this exists, and it's general relativity that provides the blueprint. So in this video, we will take a look at how to build a wormhole by first considering the general relativistic considerations. In order to manipulate spacetime, one must use general relativity as the blueprint. A little history on wormholes. In 1935, Einstein wrote a paper with Rosen on the Einstein-Rosen bridge, a connection in spacetime in which later, in 1955 and through 1957, John Wheeler coined the term wormhole. He also coined the term space-time foam, connected to wormholes. And in 1988, Morris and Thorne wrote a paper about traversable wormholes. And in these considerations, we'll think about Lorentzian wormholes coming in two flavors: inter-universe and intra-universe. One connecting different parts of our universe, and another one connecting our universe to another. They differ at the global level. For now, we'll focus on the ones that connect distant regions in our universe. The mathematical machinery in general relativity uses the absolute differential geometry, also known as tensor calculus. And space-time, space and time, are merged into this concept of space-time, which is endowed with curvature. That is the bending of space and time near an object, which is the gravitational field of that object. And the potential describing that gravitational field is the space-time metric. In the component-based notation, one commonly writes a line element as ds squared equals the metric tensor times dx mu dx nu, where x0 is the time coordinate element. Roman indices are spatial coordinates, where Greek indices are space-time coordinates, and a space-time is simply a differential manifold that has a metric defined on it. A spacetime is a four-dimensional manifold with a Lorentzian or pseudo-Riemannian metric. The metric should have the Lorentzian signature negative, positive, 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 meaning that the time component is negative, and a spacetime is often referred to as having 3 + 1 dimensions, that is 3 spatial dimensions and 1 time dimension. The manifold is a Hausdorff and paracompact manifold, for those in the know. Now, starting from the potentials, one constructs the affine connection via the Christoffel symbols of the second kind, given here with the gamma symbol. This tensor involves partial derivatives of the metric tensor, and also utilizes the inverse metric tensor with upper indices, the common notation indicating partial differentiation, and the affine connection governs the acceleration of a freely falling body in a gravitational field. Now, if one considers a small test particle free to move under the influence of gravity only, it will follow a geodesic path of the spacetime metric. A geodesic is defined as the curve that extremizes the total proper distance, that is, the variation on the action, which is the integral of ds, given here minimized to 0, using the calculus of variations. If you're interested on more about this, see some of my previous videos. Now, parametrizing a curve in terms of the proper distance and denoting the tangent to the curve by a 4 vector, the spacetime vector given here by v mu, which is dx mu ds. Then the evolution of the geodesic is governed by what's known as the geodesic equation, which is given here, a second-order equation. Noting that this equation also involves the Christoffel symbols, the affine connection. For a massive test particle, following a time-like path, the curve is more naturally parametrized in terms of proper time d tau, and d tau squared is equal to negative ds squared. By definition, a time-like curve is one that has a squared distance to be negative. A null or light-like curve has a squared distance of 0, and a space-like curve has a squared distance that is positive. For a time-like geodesic, in a Lorentzian spacetime, the total proper time is given by the integral of d tau, which is the integral of the negative metric tensor dx mu dx nu, and this is a local maximum. For a geodesic in a Riemannian space, the proper distance is a local minimum. Maximizing time, minimizing space. The Riemann curvature tensor is an expression that has the partial derivative of the Christoffel symbols as well as the square of the Christoffel symbols involved. And it is something that you should at least go through one time with a little bit of index gymnastics. This tensor governs the difference in the acceleration of two freely falling particles that are near each other. For instance, the tides are an effect of the moon's Riemannian curvature in the vicinity of Earth. The Riemann curvature tensor is where we will also develop something called the Ricci tensor. And we do this by contracting some of the indices. Again, I've done a whole series of videos on tensor calculus if you're interested in learning more. Now, the Ricci tensor can also be contracted to give the Ricci scalar, given by capital R. And again, these contractions are done through using the inverse metric tensor. The Ricci scalar measures the total curvature of the space, and it is a key feature in the Einstein field equations. So it is from the Ricci tensor and the Ricci scalar one builds the Einstein tensor g mu nu is equal to r mu nu minus 1/2 r g mu nu. The Einstein field equations relate the curvature of space-time as measured by g mu nu to the distribution of matter and energy as measured by the stress-energy tensor T mu nu. Now, explicitly, one writes the the Einstein tensor with a factor of 8 pi g over c to the fourth, and g is the universal gravity constant given here. So, in any approximately Cartesian coordinate system, it is conventional to make the components of the metric dimensionless, while the coordinates themselves carry dimension of length L. Then the components of the affine connection coefficients will have components of 1 over L, and those of the Riemann and Ricci tensors 1 over L squared. This makes the dimensions of the stress-energy tensor have dimensions of energy per volume, energy over volume. Explicitly, the energy stress tensor can be broken up into component parts. Rho represents the energy density, S sub I or S sub j the energy flux, which is generalized by a pointing vector, and pi sub ij is the stress, which is a generalized notion of pressure. The Einstein field equations can be derived from an action principle. S, given by this expression with 3 different integrals over different regions. Here we'll explain what each part is. We have the first part of that being the Einstein-Hilbert action. The Einstein-Hilbert-Lagrangian integration runs over the entire 4-dimensional region we're calling omega, and the square root of g is the square root of the determinant of the metric tensor. The second term is the Gibbons-Hawking surface term. This integration runs over the 3-dimensional boundary, and the boundary term is required for technical reasons. Many times it can be safely ignored. The little superscript 3g is indicating a 3 metric, where k is the trace of the second fundamental form, the normal derivative of the metric, or sometimes known as the curvature. the contribution coming from the Lagrangian capital script L, describing whatever matter is present, and varying the action with a fixed metric on the boundary reproduces the Einstein field equations. The stress energy tensor is given by T mu nu as a function of x, given here by the variation expression involving the integral of the Lagrangian with the derivative of the determinant of the metric tensor in the four-dimensional spacetime. Now, one notes that gravity is a weak field most of the time. And if gravity is a weak field, then general relativity can be reduced down to a linearized theory that exhibits deep analogies with the ordinary electromagnetism. If the gravity field is both weak and time independent, then modulo some technical fiddles, general relativity reduces down to Newton's theory of gravitation. Now, one notes in the weak field approximation, the metric is approximately flat. That is, spacetime is closely approximated with the Minkowski metric of special relativity. We will define that metric here with the following signature. So on the diagonal element, we have the time component -1 and the spatial diagonal components +1. So the signature is -1, 1, 1, 1. So then in approximately Cartesian coordinates, one has the metric tensor as the Minkowski metric plus an additional metric, which is a very small, negligible term. However, that small term, being really small or much smaller than 1, might not be negligible. So when we expand it out in this metric notation, we get the following for the affine connection. And the big O notation just means that second-order terms can be ignored. The Riemann tensor then follows from this formulation using our new metric. Once we've built the Riemann tensor, we can contract the indices, producing the Ricci tensor. And you'll notice the use of the box operator there. If you're familiar with that, that is the D'Alembertian operator. It's a wave operator. So a little gauge theory. Here we take advantage of our freedom to make a coordinate change to adopt what's called the Hilbert gauge. The gravitational analog of the electromagnetic Lorentz gauge given here, d mu a mu equals 0, where a is the electromagnetic vector potential. The Hilbert gauge condition is given here, and more on gauge conditions maybe later, but the math follows through that we can equivalently write it this way, and the Hilbert gauge is then the linearization of the so-called harmonic gauge. Again, this has to do with something that has to do with the duality of the field that you're considering and the symmetry being applied. This gauge linearized gives the Ricci tensor simplified here, again with the wave operator being defined in this way, with the del operator incorporated into that. Now, so from this we get the linearized Einstein tensor to be g mu nu equals this expression. And finally the Einstein field equations for the weak field approximation reduced down to this expression. A rearrangement of terms yields this expression. So now, with this we can compare with flat space Maxwell equations in the Lorentz gauge. You see, the whole purpose of reformulating that way is so that we can compare it to Maxwell's equations in tensor format. We can use the machinery in electromagnetic theory and carry that over to the weak field gravity approximation. Now, consider a point particle with the rest mass given by m sub 0 and a 4 velocity v mu in terms of the proper time tau, following a particular path y mu, which is also a function of the proper time parameter tau. The parameter tau is a proper time along a particle's world line, which is the space-time path. Then we get the stress energy tensor to be given by this expression, utilizing a four-dimensional delta function, which is merely a function that picks a certain value out. We then get the linearized field equations to look like this. So the solution to this set of differential equations, the metric h mu nu, can be extracted to be this expression, and the right-hand side is to be evaluated at the point where the particle's path y of tau intersects the past light cone with apex at x. If you're not familiar with past or future light cones, check out a video on special relativity. If the point mass were moving with a constant 4 velocity, then this expression simplifies to h mu nu equal to this expression here, where r is the distance from the point x to the particle generating the gravitational field. From this, the connection between the linearized Einstein field equations and Newton's law of universal gravitation are now manifest. More generally, for any static distribution of matter, now assuming an internal stresses are small compared to the energy density, the field, h mu nu, can be calculated in terms of the Newtonian gravitational potential phi of x. Now, going to the rest frame and adopting Cartesian coordinates, this gives us elements of our metric h in terms of the Newtonian potential phi to be this, or equivalently this.
There's no need to insult the man, just because he doesn't know how to find an interspatial flexure.
Interspatial flexure? Why didn't you say so in the first place? He said wormhole, a layman's term that covers any number of phenomena.
Strong field solutions. The full Einstein field equations are nonlinear equations, and this is the principal difficulty in extracting an exact solution. Nonetheless, exact solutions have been found. Not a month after they were published, Carl Schwarzschild found a solution for a statically spherically symmetrical, non-rotating, non-charged black hole. And later on, Roy Kerr found a solution for a rotating black hole. The Reisner-Nordstrom solutions extend Schwarzschild's solution to the interior of the black hole, if such a thing exists. Now, to get a quick and dirty approximation, one uses the ADM split. In any well-behaved coordinate patch, one can use the time coordinate to decompose the 3+1 dimensional Lorentzian metric via the ADM split. The ADM split yields the following expression, where the metric is split in terms of its time components and its spatial components. Some technical notes. The function nt of x is the lapse function, and the beta is called the shift function. The metric tensor describes the geometry of space, while the lapse function and the shift function describe how the space slices are assembled to form a space-time. And for the inverse metric, one has this from the ADM split. Noting the use of the upper indices for the inverse. The geometry of spacetime depends strongly on the choice of the time function. That brings us to black holes and their horizons. Horizons are theoretical constructs that qualitatively exhibit two salient characteristic features. 1. Horizons are one-way membranes permitting the passage of light and matter in one direction only. 2. Time slows to a stop at a horizon. But horizons come in many flavors. In fact, there are several types of horizons that occur in general relativity, typically associated with a strong gravitational field. Now, some types of horizons don't even require gravity fields. Horizons can be very strange objects, so we'll spend some time talking about them. Event horizons, or absolute horizons. These can only be obtained for a spacetime containing one or more asymptotically flat regions. That is, for each asymptotically flat region, the associated future or past event horizon is the boundary of the region from which causal curves, null or timelike, can reach asymptotic future or past null infinity. So what does this mean? Well, finding the event or absolute horizon, if one exists at all, requires knowledge of the space-time geometry arbitrarily far into the future. And anything trapped behind an event horizon is trapped for all eternity and can never get out. It truly is the point of no return. A black hole may therefore be defined as anything trapped inside an event horizon. Apparent horizons. Apparent horizons are locally trapped surfaces, So consider any closed, space-like two-dimensional surface at any point on the surface. They can use to be defined inward and outward normals on this surface. And you can define propagating wavefronts thusly. So now imagine a two-dimensional surface. If, for instance, the area of both inward and outward wavefronts decrease over time, then the original two-dimensional surface is a trapped surface, and one is inside the apparent horizon. Anything behind an apparent horizon is forced, at least initially, to travel inwards. This doesn't guarantee things behind the horizon are trapped forever. So it's a slightly different category than an event horizon. Cauchy horizons. Now, this one is associated with the onset of unpredictability. Suppose a space-like hypersurface, and some initial data specified on this surface. The initial data might be something in the way of an initial particle's position and the velocities, or the spatial geometry and the rates of change. One can solve the appropriate equations of motion to get unique predictions for some region, call it d sigma, known as the domain of dependence. The boundary of the domain of dependence is the Cauchy horizon of the surface. So for a space-like surface, sigma, the associated future Cauchy horizon is defined as the boundary of the region from which all past directed causal curves, null or time-like, intersect the surface sigma. Particle horizons. A particle horizon is an observer-dependent concept. A particle horizon occurs whenever a particle observer never gets to see or be influenced by the entire spacetime. So for some causal curve gamma, the associated future particle horizon is defined as the boundary of the region from which causal curves can reach some point on gamma. Putative horizons. If one has a natural notion of time, then the ADM split does this job quite nicely. And in every asymptotically flat region where the lapse function goes to 1 and the shift function goes to 0, the metric is given by the Kronecker delta. Associated with each asymptotically flat region, one may define a putative horizon simply by letting the lapse function vanish. Time basically slows to a stop. Now, in any spherically symmetric, but possibly time-dependent spacetime, the metric can be cast into the canonical form ds squared given by this expression here for the line element. Now, with this choice of time function, the putative horizon coincides with the apparent horizon. Now, if a black hole is gaining mass through accretion of matter, then the event horizon will be somewhere outside the putative or apparent horizon. If a black hole is losing mass, then the event horizon is somewhere inside the putative or apparent horizon. So now one considers the Schwarzschild geometry, which is the simplest non-trivial solution to the Einstein field equations. The uniquely spherical symmetric metric vacuum solution with the coordinates tr, theta, and phi. One has the line element given by this, the Schwarzschild metric, and r sub s being the Schwarzschild radius, the point at which a black hole forms. One can think of the Schwarzschild radius as the event horizon. It is convenient to absorb a factor of c, the speed of light, into the definition of the Schwarzschild time coordinate, t. Then t has dimensions of length, and also, by definition, the radius greater than 0. The Schwarzschild radius r sub s over the radius r characterizes the overall scale of the space-time geometry. Now, if one calculates the Ricci tensor for this metric, one will find that it vanishes, implying that the Einstein tensor will vanish as well. This in turn implies that the stress-energy tensor will also be 0. That is, that the region away from R equal to 0 is an empty vacuum. Taking the limit at large distances where the field is weak, the Schwarzschild radius can be related to the net mass m of the central gravitating body. So Rs is related here by 2gm over c squared, and this shows us that the metric appears to have a singularity when r is equal to the Schwarzschild radius. Now, the Schwarzschild solution does contain a physical singularity at r equals 0, and indeed the Schwarzschild coordinate system only covers part of the full space-time manifold. That is to say, they break down in a sense once you've passed the event horizon. One can explore Kruskal diagrams to explore this in detail. The maximal analytic extension of the Schwarzschild solution contains 2 asymptotically flat regions and 2 curvature singularities. So asymptotically flat regions and curvature singularities are separate ideas. The Schwarzschild coordinate patch covers half of the maximal extension. Different coordinate patches cover different parts of the manifold, and it is possible to find coordinate patches that only cover the asymptotically flat regions, and avoid the regions containing the curvature of the singularities. The Reissner-Nordström geometry does such a thing. This describes the unique spherically symmetrical solution to the coupled Einstein-Maxwell equations, gravity plus electromagnetism. The central gravitational body possesses a mass, an electric charge, and we're going to consider a magnetic charge. In the Schwarzschild coordinate system, the metric takes the form ds squared equals. Now remember that the time component is negative, plus our radial component, and then the axial and polar part of the metric. To interpret the two parameters r sub s and r sub q, one goes to large distances where the weak field limit allows one to identify the Schwarzschild radius to be this, and the squared charge radius to be given by this, where we have a combination of the electric charge and our so-called magnetic charge, subscript E and M indicating those. The electric field strength tensor is given by the local orthonormal frame capital F for both the electric field and the magnetic field. And it can be written in terms of the electric charge and the so-called magnetic charge. Now keep in mind that the Rn solution is the solution to the statically spherical symmetric solution to the Einstein field equations describing the space-time geometry around a charged, non-rotating mass. Now, by including magnetic charge or magnetic monopoles, the Einstein field equations coupled with the Maxwell equations, in other words, the Einstein-Maxwell equations, exhibit more symmetry, that is, under electromagnetic duality. So why include the magnetic charge? Well, including the magnetic charge completes the symmetric picture. It doesn't change the geometry much, and it modifies the EM field tensor so that the stress energy tensor, and thus the metric, is still sourced similarly. That is to say, by including it, it makes things work in a more symmetric way. So in the Rn formalism, capital Q squared is the sum of the squares of the two different charges. And this enters the metric function in the following way. And so the magnetic charge contributes exactly like the electric charge in shaping the space-time, just in a more symmetric way. The thing is, so far magnetic charges, monopoles, have never been observed, and because of that, Maxwell equations state that the divergence of the magnetic field is zero. But in our Rn formalism, this is not necessarily true. Now, although we have not observed the monopoles, the kicker is the experimental detection is not required. These solutions just say, if magnetic monopoles exist, here is the solution that follows. And it turns out that this is a mathematically self-consistent extension. That is, it completes the symmetry, allowing for a more elegant solution to be found. And nothing says that it can't be there. So just because we haven't found it, doesn't mean it doesn't exist. The electromagnetic field strength tensor is given in the natural orthonormal frame by the following coordinates, given with little hats. The orthonormal basis vectors are then set up by defining them as follows, involving the metric tensor. So these are the general relativistic equivalent of unit vectors pointing in the four spatial directions, the four space-time directions, respectively. And in fact, the metric tensor is the product of basis vectors in the given directions, and they make up the elements of the Minkowski metric in the orthonormal frame. So expressing tensors in terms of their components in the orthonormal basis cuts down on the clutter, making it easier to compare results with their flat space-time analogs in special relativity. Isotropic coordinates. Isotropic solutions make spatial part of the metric look conformally flat. That is, spatial geometry appears as a scaled version of the ordinary flat space. So what are isotropic coordinates? A specific type of coordinate system where space looks the same in all directions, isotropic, equal in all directions. The key property is that spatial part of the metric is conformally flat, that is, proportional to the flat Euclidean metric. We see the forms here, or in spherical form there. Using the spherical geometry more obvious and simplifies the visualization of the radial motion, for instance for the Schwarzschild geometry or wormhole metrics. Think isotropic in same in all directions, looks the same symmetrically around any point. So in isotropic coordinates, the metric in spherical form presents as follows. Rho being the isotropic radial coordinate, distance from the Schwarzschild radius. Psi of rho is going to give the conformal factor. We have spatial conformal flatness, and this is easier to match with Cartesian coordinates, better behaved at infinity or the horizon. The Rn geometry is a black hole with two horizons, an inner and an outer horizon, located by setting the time component equal to 0 of the metric tensor, and the outer horizon is an event horizon where the inner horizon is a Cauchy horizon, a predictability horizon. And it occurs at the radial horizon term here, given in terms of the Schwarzschild radius, and the charge radius as well. Remember, capital Q is a combination of both electric and magnetic charges. Now, assuming that it is not an extremal case, the outer horizon is given by this term, where the inner horizon is given by this term, for solving the quadratic form. These roots are for the metric function f of r, a radial function, and you can see that it extends the radial function of the Schwarzschild metric. The positive component being the event horizon is the point of no return. Now the minus component here is the Cauchy horizon. It is the boundary of predictability. It is the innermost surface beyond which determinism breaks down due to the infinite blue shifting of infalling radiation. Space-time here is still smooth and not yet singular, but generally unstable. And this is what perhaps John Wheeler referred to as space-time foam. Perhaps we'll get into that more later. It is possible to put the Rn solution into isotropic coordinates, defining a new radial coordinate row by the following relation. R is equal to this factor times rho. And that gives us the line element ds squared as this expression. Writing out all the components. We said this form of the metric has an inversion symmetry under this condition. And in this coordinate system, there appears only to be one horizon at rho sub h, given by this expression. Thusly, the inner horizon has appeared to vanish. But this is an illusion. Whenever there's any horizon under consideration, one must take great care to explore the full, maximally extended spacetime. The generic, static, spherically symmetric spacetime, including a horizon, that is, any spacetime of this form can be cast into the canonical form ds squared equals this. And by static we mean time independent, non-rotating. Symmetric under time reversal. Static is the same as saying the metric possesses a globally defined killing vector that is a hypersurface orthogonal time-like near spatial infinity, i.e. spacetime looks the same along the flow generated by this vector. So what's a killing vector? It's a special kind of vector field in differential geometry and general relativity that represents a symmetry of spacetime. More precisely, a killing vector field satisfies the killing equation. This condition ensures the metric tensor remains unchanged along the flow of a vector field. In other words, a killing vector generates an isometry, a transformation that preserves the distance and angles defined by the metric. Each killing vector corresponds to a conserved quantity for particles or fields moving through spacetime. And there's an art to further specifying the functional form of n and the radial part of the metric in such a way as to keep both computations and their interpretation simple. If the geometry contains a horizon, it is useful to take the lapse function to be given by this, and therefore the metric radial component to be given by this, and the line element to be expanded out as this. This metric will have horizons at value of r with the function b of the radial horizon equal to the radial horizon. The b function is a horizon function. It is useful to have various geometric quantities associated with this metric at hand for future reference purposes. In an orthonormal frame, the components of the Riemann tensor are given by this expression. These are the components of the non-zero parts of the Riemann tensor. Many of the Riemann components are zero due to the spherical symmetry. And here the primes are denoting differentiation with respect to R. The Einstein tensor is easily computed by the usual standard, but tedious manipulations. In an orthonormal frame, the Einstein tensor time component is this, the radial component here, and the rest of the non-zero components if BR is the Schwarzschild radius and phi of r is 0, this reduces to the Schwarzschild solution. Defining the non-zero components of the stress energy tensor, we get the following pieces. Rho is the energy density, tau the radial tension, and P the transverse pressure. Einstein's equations are rearranged to give the following equations. In terms of the derivatives of B, phi, tau, and if a black hole has multiple horizons, typically the outermost one is the one of primary interest. For the outermost horizon, one knows that for all radii greater than the horizon, one has a function b less than the radius. Consequently, its derivative is less than or equal to 1, and if we assume that its derivative is strictly less than 1, phi of that radial horizon is finite. The outermost horizon, the metric takes the approximate form given here. And inner horizons are typically not event horizons. Now, if one considers the generic static spherically symmetric spacetime without horizons, one then considers the general static spherically symmetric spacetime given by this equation, where if the geometry does not contain an event horizon, it is advantageous to set n squared equal to this function, and the radial metric component to be this, gives us ds squared equal to this expression. This is the metric which is chosen by Morris and Thorne for their analysis of traversable wormholes, because a traversable wormhole does not have a horizon. In an orthonormal frame, the components of the Riemann tensor are then given by this expression. And again, we're considering all non-zero components. As all other components vanish. We have then a way of generating the Ricci tensor, the Ricci scalar, and the Einstein equations. So the non-zero Einstein tensor components are given here. Equivalently, as before, we can define derivatives of the functions b, phi, and tau as follows. This system is the most useful for a model that does not contain an event horizon. Traversable wormholes do not have event horizons. Therefore, this system is most appropriate.
Initiate drop sequence. On my mark. 10, 9.
Now transfer.
8, 7, 6, 5, 4,